because we have a shorter lecture this week, I also thought it would be fun to bring the memes back. So these are some memes that I found throughout last week that I thought were worth sharing. Yeah, short lectures are nice. Okay, here's my first one. Put a band-aid where it hurts. Yeah, that was me last week. Anyways, there was a whole day where I never even went to bed. So I think I was up for like 40 hours straight. Me after the test. Yeah, I get that, Carrot. I also think I laughed harder at this one than I should have, but muscles make the body move. Give me your skin, George. Probably off the cover of like a kinesiology or anatomy book, but I thought it was pretty great. And then Mariah Carey's All I Want for Christmas Is You. Objects in here are closer than they appear. Because we know as soon as Halloween passes, Christmas is going to invade every single store. Which I love Christmas, but I also love spooky season. So hopefully that doesn't come too quickly. It already is. Yeah. Okay. So this week we are working on module 4, which is correlations. I love the gif of this cat because I feel like at this point in the semester, that's what most of us feel like. And you can relate to it, which is a pun because correlations are looking at relationships. So anyways, I crack myself up. You guys can laugh at me laughing at myself. I don't know. As long as you're happy, I'm happy. Anyways, I kind of want to do a quick recap on what we ended our last lecture with. So we went through all of the foundational information, like what are variables, what types of variables do we have, how do we classify our data, how do we classify certain independent variables, either are they within or are they between subject variables, how many dependent variables can we have, right? We talked lots of study design information. And then one of the concluding slides that I gave you guys in the previous lecture on statistical inference was what type of test you would want to use given a certain number of, or certain criteria or certain pieces of information from your study design. So as a recap of that, we were talking about what types of variables were being dealt with. In our cases, usually it's going to be nominal and ratio data, nominal data being the independent variable, with ratio data being the dependent variable or variables if you have multiple of them. We also talked about how many variables we might have and how that could potentially influence the type of test we use, who we're measuring, right? So again, difference between within subject versus between subject samples. And then lastly, we also mentioned that there are assumptions such as normality, not having any significant outliers, also, having random sampling or making sure that the samples that we collect are actually representative of the population in terms of how much they vary with the measurements that we're taking. So all of this information combined, and some of this might not make a whole lot of sense right now, but that's why I'm bringing it up again. When we put all of this information together, we come up with a decision tree for different types of statistical tests. So you can, I know it kind of looks messy, but if you follow the flow starting at dependent variables, all of the tests that we do in our class are going to have parametric dependent variables, meaning we're going to either have ratio or interval type data. Where we start to get some variation is in the independent variables. So we can either have parametric or non-parametric. Non-parametric is where a bulk of the tests that we're going to talk about in this class are going to be. So that being like a nominal type independent variable where you have a control group versus an experimental group, or a pre-test versus a post-test type situation. And then from there, we can look into how many levels of our independent variable do we have? Do we have a between or within subject design? And then we get sorted into all of our different tests. For this week, we're going to be well, this week and next week, we're kind of going to be hanging out in the area where we're going to have both parametric dependent variables and parametric independent variables, meaning that all of the data that we're looking at is measured. There's no control groups, no experimental groups. We're not manipulating any variables in particular. We're just taking a bunch of measurements, and then we're either seeing how they relate to each other by means of a correlation, or we're going to use given relationships to predict a certain outcome, which is what we do in regressions. So in terms of the decision tree, this is kind of where we're going to hang out for the next couple of weeks. If this is a little too messy, I've also put together a flowchart that helps kind of distinguish the difference between correlations and regressions. I'll probably show this next week again, just to reiterate the difference between the two, because sometimes students get them a little bit confused. But generally speaking, we're going to have, again, parametric independent and dependent variables, so ratio or interval data. And then if the goal of the test that you're performing is to look at relationships only, that's where we do correlations. Again, if you're going to be looking into predicting a certain dependent variable outcome, that's going to be where we use regressions. For correlations, it doesn't really matter which variable you identify as the independent versus the dependent variable. So you'll see at certain points in the lecture, I don't put a whole lot of emphasis on like, this is like, the relationship between the independent and dependent variable. It's very different than how we would do cause and effect type research, where we say the effect of the independent variable on the dependent variable. So correlations, I don't really see a point in distinguishing between independent and dependent variables, especially because a correlation between two variables is the correlation that you get. So how you choose to interpret it ends up being more related to the research question instead of being like, this has to be the independent variable and this has to be the dependent variable. When you're working with regressions, on the other hand, identifying dependent versus independent variables is important, because regressions end up making a model or an equation. And within that equation, you have a bunch of X variables, or your independent variables, and you're using relationships with those X variables in relation to the Y variable to end up predicting that Y variable or the dependent variable. So when we get to next week, we'll have to be a little bit more explicit on what we're identifying independent and dependent variables as, but for this week, it's a little bit more loose. I just saw a chat pop up. Would the predictions be related to the research and null hypotheses or something different? The predictions would be related to the hypotheses, but there's a lot more that goes into it. So we'll get there when we get there. But yeah. Okay. So for correlations, we have several different types that we can use in this class. Particularly, we're just going to look at bivariate and multiple, but really we're just going to be looking at bivariate, and that'll make a lot more sense when we kind of expand what you get in an output from SPSS in the correlation analysis. So correlations, most of you have heard of these before. You're just quantifying the degree of relationship between at least two variables. So bivariate correlations are between two variables alone. Multiple correlations are when you have multiple relationships that you're investigating, or multiple bivariate relationships. You just get all of those relationships clumped into one output. So that's generally how I would distinguish these two from each other. So bivariate, you just get one relationship. Multiple, you get multiple relationships. Typically, we describe multiple correlations as having more independent variables than a single dependent variable. And I think that has more to do when we start using correlations to inform regressions. So again, for the purposes of this lecture, I don't usually say like, this has to be the independent and this has to be the dependent variable. It's more, we're just interested in seeing how two variables relate to each other. But using correlations to move into regressions, it would make a difference on how you identify your variables. Partial correlations we don't really get into in this class. These do come into play when you do your regression models. So we indirectly will end up talking about partial correlations when we start talking about regressions, but we'll save that problem for another week. But basically what partial correlations do is if you have two variables, let's say variable A and variable B, when we do a bivariate correlation, we see how much overlap do we have between those two variables. And that overlap would represent the relationship of those variables. The more overlap we have of those variables, the stronger they're related to each other. With a partial correlation, we usually have at least 3 variables. So instead of just having A and B, we might also be looking at a C variable or even more than that. But in that case, a partial correlation would just say, I want to look at the relationship between variables A and B while excluding any potential relationship with variable C. So partial correlations look at relationship between 2 variables while excluding common relationships with other variables. So again, that'll come into play next week. And we'll probably talk about those a little bit more, like indirectly than directly, but they still pop up. As far as the types of correlations that we are running in this class, we do Pearson's product moment correlation coefficients, or that's what we calculate. It's also denoted by the coefficient R. You can just call these Pearson correlations. They're kind of the most common correlations that will pop up in research, or at least more common than what I've seen. The next most common is Spearman's correlation coefficient, which is like a type of ranked correlation. But we don't use those in this class. So keep it simple. Pearson's correlation coefficient denoted by R. This is for linear relationships only. That is a very important thing to take note of. It's part of the assumptions for both correlations and regressions, or at least linear regressions. Again, we try to keep it simple in this class without complicating stuff with curvilinear relationships. So linear relationships only. R, or the coefficient that describes the relationship between 2 variables, can assume any value between -1 and +1. +1 will be a perfect positive correlation. -1 would be a perfect negative correlation. And 0, which is the middle point between those 2 values, would indicate you have no relationship. The sign comes from basically the slope of the relationship. So if we can go from negative, this would be 0, no relationship, all the way to positive. So if that helps put it into a visual perspective for you, then that's how you can think about it. The actual numerical size, so the quantity of R, is going to indicate the strength of the relationship. So that's something I typically see students get confused with, is they say like the sign, or they mix up the meaning of the sign and the value, and then we throw in p-values and then all hell breaks loose. So the sign of the correlation coefficient indicates direction. So either you have a negative or positive, and we'll talk about what each of those means in a few slides. The actual value of R tells you what the strength is. Okay, so you can have strong positive and strong negative. You could have a weak positive as well as a weak negative correlation. But separate those two. Having a positive correlation doesn't mean that the correlation is any stronger than having a negative correlation. So sign and value are separate things. Okay. When would we want to use correlations? So typically these are going to be used when you want to establish an unknown relationship. Okay, and that's usually a precursor into trying to identify cause and effect. type research. So you figure out what relationships might maybe be like a confounding variable or might be a contributing factors to a certain outcome. And then you can weed out and control for some of those relationships, right? So that essentially becomes part of like your inclusion exclusion criteria, so that you're taking out any possible relationships that could be contributing to the cause and effect intervention that you end up doing. So correlations are a nice kind of stepping stone, or a foundation that you might use before you go into cause and effect research. We also could use correlations to validate different protocols or equipment. So I have an example here. If we looked at skin fold measurements versus bioelectrical impedance, and we were trying to measure a certain outcome of body fat percentage, right? We could take the two methods, figure out what a percent body fat was for a given individual or sample of individuals, and then we can take a correlation between the outcomes of each of those tests to see how closely they measure body fat. Sorry, my cat's on my lap today. But the more closely aligned those values are between those two different methods, or the stronger the correlation between those two methods, the more reliable they are with each other, or the more consistent the measurements are between protocols. Okay. Or another reason why we might use correlations is to see how well a test or a model might predict performance. So this is a method called cross-validation. We'll do an example of this with our regressions next week. But basically what it means is that you take actual measurements that you've collected for a dependent variable of interest. The regression is going to create an equation of a best fit line, or an equation or a model that includes certain independent variables that contribute to that dependent variable outcome. And then we can compare actual measurement to what the model predicted the measurement should be, and then see how closely those two values align. So again, similar with the skin fold and bioelectrical impedance measurement example, the closer our values are between the model outcomes and the actual outcomes, the closer those are, the stronger the relationship, the better the model has predicted the actual outcome. So these are just different ways that we can use correlations. The one thing I do want to point out, and I have 2 slides that segue on this particular point, in like correlations don't prove causation, and you've probably heard that before, right? But if we're looking at a correlation, we're strictly looking at a relationship between 2 variables. We're not saying that one variable causes the changes that we're seeing in the other variable. So examples being, if I wanted to look at the relationship between a person's IQ and their GPA, I can say, or generally speaking, I might be able to argue that the higher an IQ a person has, the higher their GPA should be. I can't necessarily say that having an IQ will cause a person to have a high GPA though, right? Because there are other factors that could be playing into a person's GPA, such as their motivation to do well in school, what their study habits might be, if they have financial support, right? For most of you, at least from the pre-semester survey, most of you work jobs because living costs money, right? And rent sucks in LA, or if you live in Long Beach or neighboring places, right? So if you have to put more time into work, that takes away time from school, which therefore could take away from class performance, which ends up dropping your GPA, right? We could also have the amount of time you have to study on your classes. If you have a bad instructor, right, then if you're doing more independent learning, which I've been in those situations before, where you Google everything in the class because you don't have enough information on what you actually are learning about. So if you have a bad instructor and they're just not teaching the class well, that could also drop GPA, right? You could also have parental pressure. So this isn't physics. Yeah. This isn't an exhaustive list, but it provides a nice example of how there are multiple factors that can play a role in one single relationship that you might be able to observe. And we can't actually prove or argue that we have a cause and effect kind of relationship going unless we've controlled for certain variables and applied a specific intervention or exposure to a sample. Okay. I have another example of this, and it's primarily because I like cats, and there's a GIF attached to this slide. But the same thing we just argued in the previous slide could go with looking at the relationship between leg length and pant length. Generally speaking, people with longer legs should have longer pants, right? And the other way goes around. If you see a long pants, you can expect that the person wearing those pants likely has long legs, right? But we can't say that having long pants will cause you to have longer legs. It doesn't work that way, okay? So just another example that correlation does not prove causation, okay? All right, any questions so far? Cool, all right. Pop them in the chat if you have them. I've got it open so I will be able to see. That's kind of like the foundational information on where we get correlations from. Now we're going to go into what the direction and the value of R actually mean. So positive correlations would indicate positive sign or a positive slope of a line of best fit. And we usually are going to use scatter plots to represent correlations. So I think we did this in the very first lab, and I was like, what do these variables seem like they have a relationship to each other? So you guys are pretty well practiced in actually being able to visually identify if you see a relationship or not. Now we're going to actually quantify it and then explain that in words and explain if we have a significant relationship or not. So positive correlations are all going to have a positive slope, indicating that as one variable increases, the other variable also increases. The actual strength of the relationship is determined by how closely all of these points line up into a line, or what we look at linear relationships. So the line is what we're kind of aiming for. So a perfect correlation with a value of 1 or a positive 1 would have data that line up exactly like this. Okay, that's kind of rare in the real world. So usually we say that strong relationships are going to have an R value between 1 and 0.7. Moderate relationships will have a value of 0.7 to 0.3, and then weak relationships 0.3 to 0. Okay, being greater than 0, because 0 would mean we have 0 relationship or no relationship. But you can see as the relationship gets weaker and weaker, the dots on our plot get further and further and further away from what ideally we would say is a line. But generally, when you look at all of these graphs, they do represent some type of upward trend. The same could be said for negative correlations, but instead of looking at a positive slope, we're now looking at a negative slope, right? So we can describe this as our X variable increases, we see a decrease in our Y variable. Okay, so you might have heard these terms as directly related or proportionally related as like positive correlations. Indirectly or in proportional relations are associated with negative correlations. So those might have been terms you guys have heard before. But you can see in terms of the strength or how we classify strength, the R value differences are the same as they are for positive correlations. Again, the only thing that we're changing is the sign or the direction of the trend. Okay. All right. And then for no correlations or zero, a slope of 0 or an R value of 0, that's going to be where the relationship is undefined. So this is where I don't know if you guys remember this from algebra, but when you make an equation of a line, it's y equals mx plus b. And if you look at, or you isolate out m, which is the slope, you're looking at the change in y over the change in x. And if there is no distinct pattern in the change of x, that usually results in a denominator of 0, which is undefined solution. So that's why we say a slope or a horizontal line has a slope of 0, the relationship is undefined. Way back to high school algebra. Woo! Okay. As I mentioned before, scatter plots are our best way to visualize correlations, and we can put a line of best fit or a trend line in our scatter plots. The way that the line of best fit is inserted is usually figured out by whatever software we're using, but the methodology behind putting a line of best fit in a scatter plot is that the line placement should minimize kind of the error that surrounds these little dots between that line. And we'll go into that a little bit more when we actually build regression lines and models next week, but that's kind of the method behind why we put trend lines where we do, because we're minimizing the distances between all of the points in that line. Okay. But in a correlation, the slope of the line is going to relatively be representative of the coefficient R. Questions on any of that? Cool. Okay, so now we can go into the assumptions that we have to make for correlations. This is the last point that was on the slide that I showed you guys based on like what test do we use, right? So once you figure out that you've got the appropriate variables, so in our case, we have at least 2 paired continuous variables that are ratio or interval data, or a parametric dependent variable and a parametric independent variable. Maybe we've already looked at, well, like we know we can run a correlation with just the variable information. Let's say we're already aware that we've randomly sampled our from our population, so we've got a sample that should be representative of the people it came from, right? Another assumption we always usually have to have is that we have a normal distribution, right? So our sample distribution should be relatively similar to the sampling distribution of the population with no significant outliers. Okay. From here on out, I kind of would say that no significant outliers means greater than 3 standard deviations. So if someone is either past +3 or they're below -3 standard deviations, then they would be a significant outlier. But we can still determine outliers based off of our regular methods like the IQR method. We can still check normality using our skew z-Kurt and our Shapiro-Wilk test of normality. Okay, I don't typically emphasize this process from here on out in the class, but I do like to just reiterate it is something that should be checked for all types of statistical tests, in addition to the random sampling component. And that's just because if we always are assuming that our sampling distribution of our population is normal, then our sample distribution should be representative of that sampling distribution, right? And if we have skewed data, or we've got individuals who are just like jacking up all of our stats, right? That's going to make the inference part a little bit muddy. So if our sample isn't representative of our population, we cannot infer our sample results onto what we would think or expect to see in a population. So these are the two. These two will be they're an assumption for every single statistical test we run in this class. Usually there's an assumption that's related to the types of variables that you have. So we have at least 2 continuous variables, went over that one. And then the last one is that we have to have a linear relationship. Okay, which should make sense because we're using a Pearson's correlation, which is based on linear relationships. So just to give you an idea, when we put scatter plots, the way that we usually test this assumption is by making a scatter plot. We're not even doing anything super fancy yet, but you just see, do the data represent a line or relatively a line or no line at all? And if you get something that looks like that, you can reasonably assume that the variables you are looking at have a linear relationship. If you get something else that looks curvy or parabolic, this is not a linear relationship, and in which case you would have to use a different type of correlation. There are different types of tests that will look at curvilinear relationships, but they're beyond the scope of this class, and we don't need to make things more complicated than they already are. So linear relationship is an assumption of Pearson correlation coefficients specifically. The null hypothesis for a correlation, and you guys might remember the last exam I said, once we get past this first exam, you need to remember to keep track of your null hypotheses. Hold on one second, I just saw a chat question. Will we ever have to remove outliers like how it said in the slide before, or will the data for the most part be normal? For you guys in your activities, we're going to assume that everything is normal. Whether it actually is, I don't know, because I inherited the data sets from other people or from the textbook resource. So yeah, I would say it's an assumption that you'll need to note. Oftentimes I'll ask you guys like, oh, what are the assumptions for a bivariate correlation? And then I have you list them out. That's more so that you remember that this needs to be, like this assumption needs to be recorded, and it's important for the validity of the results of the test. But I'm not gonna, I likely won't make you guys actually do this. I know in this activity I don't make you do it, but I'm trying to remember if I have any data sets where we actually readdress this again. There might be 1 or 2 when we get to t-tests or ANOVAs, but I will let you know when we get there. Okay. Okay, back to the null hypothesis for correlation. So the research question for these is usually going to be seeing, is there a relationship between an independent and a dependent variable? Or is there a relationship between 2 variables or 5 variables, or et cetera, et cetera, et cetera. So the null hypothesis, we're going to keep it non-directional. So we still have 2 tails in our region of rejection, or alpha is going to be split in half, right? And we are arguing there is no significant relationship between whatever 2 variables you're looking at, okay? If we look at the mutually exclusive statement to the null hypothesis, that would be our research hypothesis, which would argue there is a significant relationship. Remember that our statistical tests and the p-values we get are directly related to the null hypothesis. So that's why I put it in yellow. That should be the one that you remember. And it's pretty easy to come up with the research hypothesis if you know what the null is. So really, you only need the yellow part. All right. When we put our data, whatever set we have, we put it through a correlation analysis, we will get an R coefficient and we will get a p-value for that R coefficient. So if we put the null hypothesis in terms of R values, right, we just said the null hypothesis would argue there's no relationship or no significant relationship. In other words, we're arguing that R is equal to 0. right? The research hypothesis would just argue the opposite, and it would say that we're not equal to 0, so we could have a positive R, we could have a negative R, whatever, it just is not going to be equal to 0, okay? Or in other words, we could potentially have a significant relationship. P, remember, is that the probability that the null hypothesis is true, right? Or it's also representing the probability of a type 1 error. So when we would reject the null when the null is true. But we can also, if we put it in terms of a correlation analysis, we could say it's the probability that there is no correlation, right? Because it's directly related to the null hypothesis. So p-values, that we interpret them the same as we have in past examples. For the rest of the semester, our level of confidence is always going to be 95%, which means the alpha that we're comparing our p-value to is always going to be 0.05. So that'll be a nice, easy thing to remember. But remember, we said if p is greater than 0.05, we tend to accept the null hypothesis. If p is less than 0.05, we reject the null hypothesis, okay? So if we had a p greater than 0.05 for a certain correlation coefficient, we would say that we're going to argue there's no relationship because p is not small enough to reject the null. If p is less than 0.05, then we can say we likely have a significant relationship. And we go on with that information and do with it what we will, right? But I do have a note down here that the p-value is just looking at the significance of the relationship and not the strength. Sometimes I have students who are like, p-value is less than 0.05, therefore we have like a weak relationship, or they start trying to draw the p-value, like the numerical value of the p-value, they start to mix that up with the value of R. Because you can have a significant weak relationship, you could have a significant like negative moderate relationship, okay? So p-value is independent of R, or the significance of the relationship is independent of the actual strength of the relationship. So try not to get those confused. Okay, before I keep going, because we are slowly approaching the end of our lecture. Do we have any questions before I move on? Cool. So I wanted to give you guys a kind of an idea of what this will look like in SPSS. So if you don't feel like going back through activity videos to reference this, then you have picture references. I did also post the layered statistics correlation steps. Layered statistics is like an external resource that I like to use for when we start getting into statistical tests, because they actually will spell out the procedures for you, and they usually have a screenshot with examples of like variables from their own data sets. So that's posted in the checklist under the supplemental materials section. So if you like picture references, I will be posting those for pretty much all the tests we have for the rest of the semester if you like to follow the examples they have in there. But once we get our data all set up in SPSS and we have everything set to scale, right, scale data, so we're indicating we have ratio or interval data, the steps to actually get to the correlation analysis is going to analyze, correlate, and bivariate. Super, super easy to remember, okay? Once we get into the analysis setup, it'll ask you, like, all of the variables you have in your data set will be in the box on the left. And then whichever ones you want to actually analyze, you just put them in the box to the right where it says variables. So this one has 2 variables. You could have 10 variables. You could have 50 variables. Honestly, doesn't matter how many, as long as you have at least 2 in that box, the correlation analysis will work. We're doing Pearson correlation coefficients, so that's the only box that should be checked. We're also looking at 2 tails as far as our test of significance. And then this last little box just that says flag significant correlations, that will just put an asterisk next to any of the p-values that are less than 0.05. So that's what that box does. As far as options, we don't really deal with that. The only thing that this does is it allows you to change the level of confidence that you want for your test. So like I said, we're going to do 95%. That's the default in SPSS. You don't really need to touch that. After you put the variables in, you say, okay, click OK. Okay. And then you'll get an output that has a correlation matrix. Now, the matrix is either going to be really small, right, if you only have two variables, or it could be potentially really large. But the setup for each variable comparison is going to look something like this, where it has a Pearson correlation coefficient, which is your R value. Underneath that, it will have the P value, which is associated with the significant value. Honestly, I don't know why they don't just put P in SPSS, but SIG always represents you have a P value. And then N is going to be the number of paired observations or the sample size. Now, the reason we term this as paired observations is that each of your variables, if you're looking at a relationship between like, well, this person has a height and a weight, and we put them together, and that point is where they meet up, right? You have to have two measurements for the same subject in order to have a paired observation. So that's why we say paired observations, but it's really just your sample size. Okay. So this is how it's set up. If we look at this is an actual output from SPSS, so we could see we've got two variables. For this particular example, it was looking at the time spent watching TV and its relationship with the person's cholesterol concentration. So you'll notice we have if we follow this row across, we have time and TV and time and TV. So that would be comparing the same variable to itself, which we don't end up getting a correlation for because it's kind of pointless to compare the same value to itself. And it doesn't really give us a whole lot of meaning. So there's going to be some redundancy in variable comparisons. But then we can see if we look at time spent watching TV and cholesterol, we have a Pearson correlation coefficient R, which comes out to be 0.371. And then we also have our SIG row, which is our p-value, which in this case, it says 0.000. And I posted this example because you can never have a 0% chance of error, right? Because remember, P is always going to be in relation to how much type 1 error did we possibly make? And you never have a 0% chance of error. So whenever you write, or if you get something like this in your output, SPSS sometimes will automatically change this to P is less than 0.001. But in the case that you get something like this, when you report your p-values in your answer sheets, make sure you change this to less than 0.001. The reason being is that SPSS is limited to 3 decimal places when it reports the output. So this could be 0.0001 and the 1 doesn't show up because it rounded downwards. So never report P is equal to 0. P is always going to be less than 0.001 if you get something that looks like this. But the interpretation that we can get from this R and this p-value, right? Since P is less than 0.05, we know we have a significant relationship. And our interpretation would be worded something similar to this, right? So we have, there was a statistically significant moderate positive correlation. So the moderate positive is coming from the R value. The significance is coming from the P value that we got. And then we just describe what the relationship was between. So in this case, it was daily time spent watching TV and cholesterol concentration. This particular example, they included their sample size, so males aged 45 to 65 years old, and then they reported their statistics. We don't worry about reporting them in this way, but they were just indicating R with degrees of freedom of 98, which is Usually for this, it's going to be the sample size minus however many variables you're comparing. So in this case, 2. So 100 minus 2 is 98. Don't worry about degrees of freedom for this class, for correlations. It gives us what R was equal to and then how confident we were in the relationship, right? Or if we noted it as significant or not. So this is what you might see for a bivariate regression. For a multiple regression, you set the test up the same way in SPSS. You're just going to have more than 2 variables. And you'll end up getting a correlation matrix that looks something like this. I made this one in Excel because it was a lot easier to fit on a slide. We'll practice making a correlation matrix in Excel in your activity, but you surely will be able to visualize multiple correlation or correlation matrices in SPSS as well. They'll look pretty similar to what we had on the previous slide. You're just going to have a lot more variables than 2. So, but the setup will still give you a p-value and an R coefficient and the sample size. So those 3 characteristics are still going to be the same, whether you have 2 variables or whether you have more than 2 variables. But a couple of things I wanted to point out in a correlation matrix that has multiple variables is there's going to be this diagonal line down the center of correlation coefficients that equal 1. And those are just going to represent all of the direct relationships between the same variables. So we can see weight and weight, BMI to BMI, right? And remember we said that those correlation coefficients of 1 don't really carry any meaning to our actual analysis. But if we use this diagonal, we can see that 1/2 of this I grayed out or put in a gray color, and that's because the values that you get in the top half of the matrix are redundant with the bottom half. So when you read these, especially in SPSS, because there's going to be a lot of numbers, I would identify where the diagonal exists and then either choose to read the top half or the bottom half. That way your brain isn't getting overwhelmed with how many numbers are on the table, because they can get a little bit crazy sometimes. But just know bottom half is redundant with the top half. Okay. And then again, I just put an extra note on the other slide that the values on the diagonal represent bivariate correlations between the same variable. So again, they don't mean anything to us really. The last variable I wanted to talk about today is the coefficient of determination. And this is represented by R squared. In SPSS, it'll be shown as a capital R. If you put a lowercase r, honestly, it really doesn't make a difference. So R squared is the correlation coefficient squared. We also refer to the coefficient of determination as covariance. And what these 2 terms mean is that it's basically representing the common variance or the percentage of variability that's shared between 2 variables. So if we did a bivariate correlation between 2 variables and we ended up with an R coefficient of 0.7, we square that and we end up getting 0.49. So that's our, in this case, R squared, or our coefficient of determination or covariance, is 0.49. We can turn this into a percentage, so just multiply it by 100, and then we can see what our interpretation of that variable would be, which is 49% of the variability in one variable is explained by its relationship with the other variable. The rest of the percentage, or 100 minus the 49%, you could also do 1 minus 0.49. Either way, you'll get the same answer. Right, the rest of that percentage that's not accounted for is the probability the relationship is due to chance or other factors. So let's say that we were looking at IQ and GPA, right? And we got a R of 0.7 as the kind of strength of the relationship between IQ and GPA. Okay, we could say that 49% of a person's GPA is determined or explained by its relationship with a person's IQ. Okay. The rest of the 51% that we haven't accounted for could have been due to study habits or the instructor or like financial support, all of those other variables we listed in that one slide. Okay, so that 1 minus r squared is our coefficient of non-determination. That's the accounting for the fact that we could have made an error, or there's other factors that we just haven't considered in the relationship we are investigating currently. Okay. This will really come into play next week. So we'll give you guys the first week to kind of settle with the idea of what r squared means. And then I'm kind of going to rip you apart next week, probably when you actually have to use this when you're building regression models. So this is a nice like toe dip into coefficient of determination. Just so you have another example with variables that are actually written out. This is the same table that I gave you guys as an example for what the correlation matrix looks like in the SPSS output. So from this, I have highlighted what my R value was, and it was 0.371. I can square this value to get my coefficient of determination, which ended up getting 0.14, or if I multiply it by 100, it's 14%. So interpretation of that R squared value is daily time spent watching TV statistically explain 14% of the variability in cholesterol concentration. Okay. If we look at our coefficient of non-determination or do 1 minus r squared, right? So I've typed out we can either do 1 minus 0.14 in decimal format, or we can do 100 minus 14% in percentage format. We end up with 86%. And that would be interpreted as 86% of the variability in cholesterol concentration is explained by error and or relationships with other variables. Okay. Questions on that? I'll open the chat box just in case.
So this one means that it wasn't correlated with TV. It was other factors in this example.
Oh, so I'm glad you phrased it that way, because we still have a significant moderate correlation. So the two variables we're looking at are still significantly correlated with each other. We're just saying that the contribution for the coefficient of determination, the contribution of the variability that we see in cholesterol is due in part, for 14%, is due to its relationship with time spent watching TV. Does that make sense?
Yes.
Yeah. And I don't want it to sound like we're looking at like 14% of time spent, or 14% of cholesterol concentration was caused by an effect of like time spent watching TV. That's not what we're saying, right? We're just saying that the variability that we see in cholesterol concentration can be explained by time watching TV. And that we're quantifying that explanation at 14%. And that's based on whatever sample they used. But again, we're looking at probabilities or likelihoods. So that was a very good question to ask. Okay. If coefficient of determination isn't making a whole lot of sense with numbers, we do often use Venn diagrams to explain. So if it helps to draw out relationships on a piece of paper when you're doing your assignments to help kind of clarify what covariance is, you could draw a Venn diagram. And the area of overlap that you see between two variables, so in this case, variable A and B, that overlap is the coefficient of determination, right? So we have R, or our relationship squared, gives us the percentage of overlap that exists between two circles. That's another way you could think about it, okay? So if you have no overlap at all between two variables, that would mean 0% overlap. So R would be 0, or R squared is 0, right? So when R is 0, there is no relationship. So if you have 0 overlap between variables, or a 0% value for r squared, your variables are not related to each other. Or 0% of the variance you see in one variable is due to its relationship with the other variable. If, however, you have full overlap, that would indicate a perfect correlation, right? So if all of our variability, our Venn diagram ends up being one circle, that means that r squared is 100% or it has a value of 1. We took the square root of 1 and worked backwards. We either have an r that is perfectly positively correlated or perfectly negatively correlated. Okay, so Venn diagrams, I've had some students who were like, oh, drawing it out really helped me visualize. So if you like drawing and that helps you, try it out, see if it works. If it works, keep doing it. Okay. But that is it for today. Told you we would end early. Ooh, ooh. Okay. So any questions before we leave? Okay. I'm gonna stop sharing. You guys are free to go. If anyone has any questions, I can stay on for a little bit longer. But other than that, I will see you next week.